Welcome back to the Deep Dive. Today, we're looking into the work of someone whose career just explodes across different fields. Philip McCord Morse, 1903 to 1985. I mean, this is someone who gave us a key equation in quantum chemistry, wrote the go-to books on sound and vibration, and then somehow used that same thinking to help the U.S. Navy hunt U-boats in World War II. It's kind of amazing.
It really is. And if you've ever had that feeling, that the deep rules of how things work should apply just as well to tiny molecules as they do to big organizations, well, Morse is your guy.
Absolutely. He seemed obsessed with a few core questions, didn't he? Things like, what's the main pattern of movement here? How does the container, the boundary, shape what can happen? And, maybe most critically, where's the lever we can pull to make things more stable, more coherent, and less leaky?
That's exactly it. Our mission today really is to show you that Morse wasn't just flitting between problems. He had this single, powerful framework. He looked at everything, atoms, concert halls, naval fleets, as a problem of structured motion defined by its boundary. His whole approach was about turning messy reality into a solvable mode problem.
A mode problem, okay.
Yeah, essentially a way to engineer stability.
So before we dive into the specifics, let's maybe lay out some of the key terms from his work, the lens we're calling motion theory, or MT.
Good idea. The big shift in thinking is this. Structured motion is the fundamental thing. It's primitive. Time, then, isn't absolute. It's just the rate a pattern updates or repeats.
Okay, time is a rate of change.
Right. And fields, they're just gradients in that motion. And mass itself is basically resistance to changes in motion.
Yeah, that reframes quite a lot. But let's focus on stability, because you said that's what Morse was always trying to optimize.
Exactly. For Morse, stability keeping a desired pattern going, it's all about balance. We can boil it down to three things. High synchronization density, let's call it S.
S for synchronization. Got it.
Low leak, which we'll call R. Think of R as randomness, noise, or energy escaping the pattern.
Okay. S high, R low.
And the third is shaped coupling, C. That's how the parts of the system interact, or how you influence it from the outside. The result of this SRC interplay is the system's spectrum. It's allowed modes, it's possible frequencies, it's like the system's ID card.
Yeah.
If you know the spectrum, you really understand the structure.
Hold on, let me try to make that concrete. Say you have a band playing. S is how well they play together, hitting the right notes at the right time.
Perfect.
R, the leak, is maybe the room acoustics are bad or someone hits a wrong note, distracts us.
All of that. Anything that degrades the intended pattern.
And C, the coupling. That's like the conductor or the sheet music, the rules they follow to keep S high and R low.
That's a fantastic analogy, yes. And Morse's genius was applying that same SRC thinking across, well, mind-boggling scales, like 18 orders of magnitude difference.
Wow. Okay, let's start small then. The molecular level. You mentioned quantum chemistry. His 1929 potential function is pretty famous, right? What was wrong with the picture before Morse?
Well, before Morse, the standard way to think about two atoms bonded together was like a perfect little spring, a simple harmonic oscillator, easy math, but
not real chemistry.
Not at all. Two big problems. First, a perfect spring means the energy levels for vibration are perfectly even, like climbing a ladder with all the rungs exactly the same distance apart. But real molecules aren't like that. They show anharmonicity. As you add energy, the bond stretches, it gets a bit looser, and the energy levels get closer together. The rungs shrink as you go up.
Okay, so the perfect spring model missed that anharmonicity.
Yeah.
What was the second problem?
Even worse, a perfect spring never breaks. You could pump infinite energy into it, theoretically, and it would just oscillate faster and wider forever. Real chemical bonds, obviously, have a limit. They snap, they dissociate.
Right. You pull them too hard, they break apart. So Morse needed a model that allowed for that.
Exactly. He came up with this mathematical function, the Morse potential, that behaves like a spring when the atoms are close to their happy equilibrium distance. But as you pull them apart, the walls of the energy well flatten out. Imagine a valley. The harmonic oscillator is a perfect parabola. Morse's valley has sides that level off at a certain height. That height, that plateau, is the dissociation limit. It tells you exactly how much energy it takes to break the bond.
Ah, so it gives chemists real numbers. The bond strength,
Yeah.
the ideal bond length, and how stiff it is.
Yeah.
But what's the MT connection? How is this about coherence?
It's all about coherence. That Morse curve is a coherence landscape. Down near the bottom of the valley, the bond is stable. That's a motion loop, the atoms vibrating back and forth with really high S synchronization and almost zero R leak. the tight, stable pattern.
Okay.
But as you add energy, you push the system up the walls of that valley. The vibration gets wider, the bond gets softer. You're moving into regions where the restoring force is weaker. The leak starts to increase relative to the synchronizing force.
And dissociation happens
When the energy is high enough that the system reaches that flat plateau, at that point, what R overwhelms S leak wins. The coherent loop breaks, and the atoms just drift apart into free, unconstrained motion. The structure dissolves.
Wow. So the very existence of a molecule is this constant balance act between S and R, defined by the shape of that potential well.
Precisely.
Okay, so from the incredibly small to, well, things we can actually hear and touch, Morse took the same thinking boundaries, modes, leaks, and applied it to acoustics and vibration. How does that even work? Going from two atoms to, say, a vibrating ship hull or a room full of sound.
It sounds like a leap, but mathematically it's less strange than you'd think. Whether it's quantum waves for electrons, or sound waves in air, or vibrations in a solid, they all obey wave equations. And those equations are always constrained by boundaries. His books, like Vibration and Sound, or the big one, Theoretical Acoustics, they essentially provided the blueprint: how to analyze vibrating plates, cavities, pipes, even something as complex as sound in the ocean.
And the method was always the same kind of pattern.
Pretty much. Step 1, figure out the geometry and the boundary conditions. What are the walls made of? Are there openings? Step 2, use mathematical tricks, like separation of variables, to break the complex motion down into simpler modes. Step 3, if there's a source, someone talking, an engine running, represent its effect using something called Green's functions.
Okay, Green's functions is a way to inject the source. And the answer you get out is always in terms of these modes.
Always. The final solution is expressed as a sum of these allowed patterns of motion, these modes. And crucially, each mode comes with a quality factor, a Q factor.
Q factor, that measures the leak, right?
Exactly. Q is the inverse of leak, essentially.
Right.
A high Q means the energy in that mode sticks around for a long time. Low leak, low R. Think of a tuning fork. Very high Q. It rings clearly for ages. A low Q means the energy dissipates almost instantly. High leak, high R, like hitting a pillow. Thud. Gone.
This whole philosophy seems baked into that famously challenging textbook you wrote with Feshbach, Methods of Theoretical Physics. People say it's less a textbook and more a way of thinking.
That's a very good way to put it. It is a philosophy disguised as math techniques. The core message is, to solve a physical problem, first, choose coordinates that match the system's symmetry. Don't fight the geometry. Second, find mathematical transformations that untangle the motion, that isolate the fundamental loops or modes. Third, and this is key, treat the boundary conditions not just as limits, but as an operator.
An operator. What does that mean practically? Treating a wall like an operator.
Think of it like this. The boundary actively selects which modes get to live and which ones die out immediately. Take a saxophone again.
Okay.
The tube length, the metal it's made of, where the holes are, the shape of the bell. Those aren't just passive containers. They form the mathematical operator that dictates which frequencies of air vibration will resonate strongly and which won't. Changing the material changes its impedance, how it reflects or absorbs sound. Opening or closing a key changes the effective geometry. That operator actively shapes the sound, allowing only certain coherent loops, the notes, to survive with a high Q.
So we can look at almost anything with boundaries. A concert hall, a sonar dome, even maybe a noisy city street, as a kind of coherence theater. The walls, openings, materials, they are all setting the Q factors for different sound patterns, determining what echoes and what fades.
Precisely. That's the concept that has aged incredibly well for Morse's work. The boundary-picked spectrum. Reality is just full of these containers and channels, cavities, waveguides, filters of all kinds. Morse gave us the tools to calculate the allowed loops, modes, and their lifetimes, Q factors, within those boundaries.
Okay, this is where it gets really wild for me. Morse looks at calculating vibrations in metal, and then he looks at ships trying to cross the Atlantic during a war and says, same basic problem.
He basically did. That's the origin story of operations research, or R. During World War II, he headed up the Navy's operations research group. And his genius insight was deceptively simple. Treat the entire theater of war, or later, you could apply it to a factory, a hospital, an airline, as a complex system of many coupled motion loops operating in noise.
Wow, that sounds almost too simple. Treating human decisions, enemy actions, weather, like modes in a machine. Surely that breaks down fast.
It's definitely a simplification, and we'll get to the limits. But the initial power wasn't imperfectly modeling human psychology. It was about quantifying flows, probabilities, and outcomes in a system dominated by chance and limited information. The goal was practical. use physics-style calculations to figure out how to optimize policy given real-world constraints.
Okay, so applied coherence engineering, but on military strategy. Policy changes driven by SRC calculations. Could you give a concrete example or two?
Absolutely. The classic one is convoy protection against U-boats. The U-boats were the main source of leak for the convoy system. Morse's OR group didn't just guess about ship formations, they calculated optimal spacing between ships, optimal zigzag patterns, Y, to deliberately shape the coupling, C, within the fleet. The goal was to raise the synchronization density of the convoy, making it act more like a single, harder-to-predict unit, while simultaneously increasing the leak for the attacking submarine.
How would that increase the sub's leak?
By minimizing the time window where the U-boat had a stable firing solution. Make the target harder to track consistently, make its attack loop less coherent, more leaky. The policy, the formation, the zigzag became the physical device controlling the interactions modes.
Okay, that makes sense. Any others?
Search theory is another huge one. A plane goes down in the ocean, a ship is lost, you have limited search planes or ships, where do you look? Morse's teams developed methods to allocate search effort based on probabilities, where the target might be, and the known detection capabilities of the searchers. They weren't just flying randomly. They were tuning the search policy to maximize the chance of a hit while minimizing wasted effort, essentially optimizing a function like lambda, text false alarm. It was early signal detection theory, framed as optimizing search patterns.
That really brings the MT translation home. Or treats policy decisions, rules, procedures, resource allocation, as ways to set boundaries and shape couplings. Good policy makes the good loops, supply lines, rescues, stable and coherent, high S, and makes the bad loops, losses, attacks, congestion, unstable and leaky, high R.
Yes. Morse effectively took the mathematical machinery for analyzing vibrations and acoustics, that whole Feshbach methodology, and turned it into a calculus for making better decisions when faced with uncertainty and noise.
It's a brilliant framework, and the core ideas still feel incredibly relevant.
Yeah.
But where did those initial physics-based assumptions start to run into trouble when applied to the complexities of the real world, especially with people involved?
Yeah, the idealizations definitely had limits. I'd say there are three main areas where the simple model started to fray, and where modern approaches, informed by MT, have had to extend the work. First, that focus on simple single modes. Morse's math often worked best when you could isolate one dominant pattern. But real systems, busy rooms, complex machines, actual economies are usually messy. Modes overlap, they interact nonlinearly, they're strongly coupled. So a big focus now is on understanding mode coupling. You can't just analyze one vibration in isolation.
Okay, reality is more tangled than the simple models assumed. What else?
Second, those perfect boundaries we talked about. Rigid walls, perfectly absorbing surfaces, they don't really exist. Morse gave us the math to handle complex boundaries, but the application often simplified them. So modern MT really emphasizes measuring the actual boundary impedance, how it really reflects, absorbs, or transmits energy, and treating that measured property as a complex boundary operator. Let the data tell you how leaky or reflective the boundary actually is. Don't just assume it's perfect. The Q factor tells you the truth.
Makes sense. Measure the real leakiness. And the third area must be people.
The human element, exactly. Or policies, especially early on, sometimes treated people like passive cogs in the machine. They assumed the system would react predictably to a new rule, but people adapt. If you implement a policy to optimize something, people will figure out how it works and change their behavior, sometimes in ways that completely undermine the policy or create new, unexpected problems, leaks. So now we try to model agents not as fixed parts, but as learning loops themselves. Effective policy design has to anticipate and include feedback and adaptation.
Right. So the lesson for anyone listening is that this isn't just history. This Morse framework, updated with mode coupling, real boundaries, and adaptive agents, it's still the playbook.
Absolutely. It's being used right now. Think about designing quieter cities. You can use Green's functions, just like Morse did for sound, but feed the model with measured acoustic impedances of building facades and road surfaces. That lets you predict noise hotspots. That's coherence control for urban soundscapes. Or look at the Coast Guard refining its search and rescue models. They constantly update probabilities based on new information and past results. That's dynamic optimization of search patterns. It's applied coherence control, continuously trying to maximize S, finding the target, and minimize R, wasted search time.
So Philip Morse didn't just solve specific problems. His legacy is this incredibly robust workflow for tackling complex systems, a workflow that civilization keeps using. Define the system, understand its boundaries, figure out its modes and leaks, and then design interventions policies to shape the outcome.
I love those concise takeaways from his perspective. Boundaries don't just fence motion, they tune it. That's powerful, and maybe even more relevant today. In noise, good policy is a physical device. It actively shapes reality. It really does. And that universality, it pushes us to think further. If Morse's method works for concert halls and convoys, why not other complex, boundary-defined systems, like, say, the human brain? Imagine treating a specific area of the cortex like one of Morse's acoustic cavities. You could theoretically measure its boundary impedances, how strongly it's connected to other brain regions. Then you could compute its expected spectrum of activity. What patterns of neural firing, what modes of thought would naturally get amplified or sustained within that structure under certain conditions.
That's a fascinating, if challenging, idea.
Well, here's the challenge for you, listening right now. Think about a complex system you're involved with. Maybe it's your team at work, a project workflow, maybe even a recurring difficult conversation you have. Can you try to analyze it using Morse's lens? First, define its boundaries clearly. Who or what is in, what are the rules? Second, try to identify the leak. Where does energy, focus, or progress get lost? What's its effective cue? Third, could you design a policy, a change in structure, communication rules, the coupling C, that would strengthen the loops you want, high S, and dampen the ones you don't, high R? That's putting the Morse legacy into action right where you are.